Hey guys, so we're going to be doing two problems here on special systems. So we're solving systems of equations, but these are two particular systems that don't typically occur that often. Those are systems that have no solution or systems that have infinitely many solutions. All right, so let's get started. Now the directions here says solve each system by graphing and check it algebraically. So that's what we're going to do. We're actually going to graph it on a separate paper. I've got my graphing paper here. We're going to do it on here in a second. But I'm going to first change this to slope-intercept form. And then we'll just do it the regular way that we've been doing it like we did in the last lesson, in the last video. But let's change this to slope-intercept form. Remember, slope-intercept form is y equals mx plus b. Let me see if I can get a different color here. Doing colors today. All right, so the slope-intercept form is y equals mx plus b. Okay, where m is the slope, b is the y-intercept. On the first equation here, so if we have negative 2 plus 6y. All right, let's see if I can get this going here. So we want y to stay on its own, right? To stay on the left-hand side like here. We want to put x on the other side where the 12 is, and then we need to basically get rid of that 6. Okay. So let's do that. So we're going to add 2x to both sides. We've got 6y equals positive 2x plus 12. We're going to divide both sides, everything by 6, because we're going to get rid of it here. So this is y equals 1/3 x, or 2/6x, or 1/3 x, plus 2. That's the y-intercept. That's the slope. So it looks like it's going up 1 over 3, I believe. Okay, let me make sure I double check this, make sure I did this correctly. Yeah, okay, did it correctly. All right, and this one here, this is x minus 3y equals 3. All right, so we're going to subtract x from both sides. So we've got negative 3y equals negative x plus 3. Then we're going to divide everything by negative 3. So it'd be y equals, no, this is negative 1. So negative 1 divided by negative 3 is just basically 1/3. Now if you have a negative on top, negative on the bottom, that's going to be a positive 1/3 x. And that's plus 1. So you can see here, or is it, no, I'm sorry, it's minus 1. My bad, minus 1. Sorry about that. Okay, so you can see here the slope is the same, but the y-intercept is positive 2, and the y-intercept is negative 1. So if we graph that, positive 2 is right here, negative 1 is right here. So they both have the same slope. Go up 1 over 3. So up 1 over 3. 1, 2, 3. Up 1 over 3. 1, 2, 3. And so basically you've got a situation where they're both parallel. Okay, let's see if I can use another marker as a ruler, since my ruler's not here. Actually, wait, I've got one. Shoot, I forgot about this protractor. Sorry about that. All right, so basically you got this, and you've got this. I probably should have created maybe a few more dots, but this is it. So these lines are parallel. They'll never intersect each other, so there is no solution. Okay. On number 2, and we'll come back. We'll actually solve this algebraically in a second. Let's just take a look at this using graphing for a second. All right. So same thing, slope-intercept form for number 2. All right. So we're going to move. Basically, there we go. We're going to take the 15x and put it on the other side. So let me write it up like we have it here, so that we don't lose anybody. Then we got 3x plus y equals 1. Again, you want this in slope-intercept form. Slope-intercept form is where y is all by itself. You've got mx, got the slope times x, plus the y-intercept. All right? So we want y all by itself. So that means in the first equation, we're going to get rid of the 15x. We're going to subtract it from both sides. So I've got 5y equals negative 15x, or minus 15x plus 5. Then I divide everything by 5. So y equals negative 3x plus 1. And over here, we're going to subtract 3x from both sides. Y equals negative 3x plus 1. And if you notice, they're the same exact equation. They're both going to be right on top of each other. Okay? So let's graph it. I mean, you're basically just graphing one equation here. So you're at positive 1. You're going down 3 over 1. 1, 2, 3 over 1. And that's it. So both equations are going to fall on the same exact line. And that is it. So in this situation, there's more than one solution. Typically, lines, when they cross each other, they're going to cross each other at, at one point. But here, because they're on top of each other, they're going to basically fall on top of each other at every single point on this line. There's so many points that both lines cross each other at because they're essentially the same line. So that's infinitely many solutions. I call it IMS, since I lazy. All right, so that's it. That's it on that. And so let's take a look at algebraically. So let's take a look at it. Obviously, we're not going to graph it every single time. Okay, we're not change it to the slope-intercept form. This is too much. Okay, this is too much work. You don't want to be doing that. What you want to be doing is doing this algebraically. So algebraically, basically, you want to pretend like we're going to be eliminating this. We could substitute using the substitution method, but we're going to use the elimination method because we know that if I multiply the bottom by 2 and add these two, this will cancel out. So I'm going to multiply the bottom by 2. So I'm going to take my red pen, and I'm not going to rewrite this. I'm just going to go ahead and put 2 here, parentheses here, and go ahead and multiply. 2 times x is 2x. 2 times negative 3y is negative 6y. 2 times 3 is 6. And then what I'm going to do is I'm going to add this equation plus this equation, because this one has changed to that one. That's basically what happened here. So when I add them, well, what happens? Negative 2x plus 2x is 0. 6y plus negative 6y, 0. So I've got 0 here, I've got 0 here, equals 12 plus 6 is 18. Well, 0, 0, 0 plus 0, 0, whatever you want to call that, does not equal 18. Okay, that's not possible. So what that means is there's no solution. If there's no x, there's no y, there's no solution. Now, if this was a 0, if we had all zeros across the board, then it would be infinitely many solutions, because it could be pretty much anything at that point for those ordered pairs. So whatever ordered pair fell on that one dot, on that one line here, let's say like this one right here, for example, right? 1, negative 2, that's going to work for both equations, all right, when we get into number 2. So, number 2, let's algebraically figure that one out. So we're going to multiply the bottom by negative 5. If I multiply the bottom by negative 5, I'll get rid of that x, and that's the goal. The goal is to get rid of one of the variables. I'm not really even paying attention to all this. I'm just paying attention to what I can get rid of first. So this is negative 15x, negative 5y, negative 5. Now when we combine all that, well, if we add this plus this, let's see what we get. This is going to cancel out, that's 0. This is going to cancel out, that's 0. And this is going to cancel out, that's 0. So this actually works out, unlike this one up top here. There's no 0, 0, 0 does not equal 18. But 0 does equal 0 here. So this actually works out. So this is infinitely many solutions. Infinitely many solutions. And like I said, this ordered pair here that we graphed earlier, like this is one ordered pair out of infinitely many solutions that will fit that equation, 1, -2. And if you want to check it, so 1, -2, this is your x, this is your y, right? So if you plugged it back in, right? So 15 times 1 plus 5 times -2, does that equal 5? Right? So you plug it back in, let's find out. So 15 plus, this is -10. Yes, that does equal 5. That works out. And if we plug this one into the other equation right here, the one that we didn't modify to get to here, 3 times 1 plus -2, I put that in parentheses because you get that plus there, and then equals 1. Well, let's see, 3 times 1 is 3. 3 plus -2, which is the same thing as saying 3 minus 2, is 1. That is true. That works out too. So you can see it works out in both equations. Okay? Infinitely many solutions. All right. Hopefully that helps. Let me know, and I'll talk to you guys later. God bless. Bye-bye.